I should probably repeat it with the recording on. So let me just repeat what I just said. The quiz is not today. It's going to be on Thursday, April 1st. It's not going to be an April Fool's joke. It will just be a real quiz covering chapters 14, 16, and 17. So it's not today. And once again, we'll be finishing up chapter 17 today and going into chapter 19. Starting next time, I'll be introducing you to a software program called StatKey. So it's important to attend this session to learn how about StatKey. We'll be using StatKey quite often for the rest of the course. So it'll be used in place of formulas that normally statistics students learn to do what's called inference. Inference meaning that we take information about a sample and we generalize it to an entire population. So instead of using formulas, we're going to be using this special software, which is very easy to use, and it's called StatKey. All right, so we'll start doing that on Thursday. Okay, any questions about our schedule? All right, so let's get started, and we'll go into back in this chapter 17. I believe we started it last time, and if I'm not mistaken,
we only got, I'm sorry, Professor, good morning. We only got one test left before the final, right?
Right.
All right.
Right, just one test left. So whatever is left will be covered before the test. The test will be near the end of the semester, probably the last day of this semester, before the final. Okay. No, that's actually that brings up a good point. The final exam is going to be on Tuesday, whatever that first Tuesday is in May. And I think, if I'm not mistaken, it's the 4th, I think, or the 3rd, I'm not sure. Whatever that Tuesday date is, you should have received an email that that is the final exam that day. All right, and it's from 8 a.m. to 10 a.m. Now, it's very important that you take the final that day. All right, it's very important. You cannot just make a last minute change, anything like that. You cannot take the final after that day. You must take it that day. Now, if for some reason there's a conflict between some other thing that you're working on for another class and all, you must take it early, not late. All right, it must be taken early. Now, if there's for some reason there's some medical emergency, God forbid it's COVID or a family member has COVID or whatever it might be, and you're not able to take it on Tuesday. Number one, it has to be a medical emergency for you. All right, that's what's the most important. It has to be a medical emergency for you, your medical emergency, because the only way that you'll be able to finish the course is you'll need to apply to Rowan University for a medical incomplete. All right, you'd have to contact the university, and then at a later date you could take the final. All right, that's the only way that you'll be able to take it later. All right, no other situations will work unless Rowan gives you a special incomplete status because of your situation, which is possible, but you would have to request that from Rowan, not from me. All right, so please, I know this is an early class, make sure that you get up in time. All right, you can't come to me and say, oh, I overslept. That's not going to work for the final exam. Also, it's not going to work also for your last test, because we are running out of time at the end of the semester. You cannot just decide I'm going to take it at a later time, or I'm going to go on vacation, or whatever it might be. No, none of that will work. You have to take the final test that day. And if you know ahead of time you're going to have a situation, you must take it early. Now, if you're sick, if with COVID, again, it's the end of the semester, so you can request a incomplete. Now, by the way, the only way you get an incomplete for medical reasons or whatever other reasons is because you are would be if you are actually passing the course. If you're failing the course, they will not give you an incomplete. All right, that's the way it works. Any questions about that? So please,
I have a question, Professor.
yeah, go ahead.
So it's not like we could take it before we come to class. It's not like we log in just like now, like the other test is, and we could take it before. Is it gonna be like open on?
It has to be, yeah, it has to be during our class.
Oh, our class. Okay.
Yeah, unfortunately, this is not an online class. It's considered a synchronous remote class, which means you must take the tests and quizzes, everything during the class period. So whatever the assigned final exam period is, that's when you have to take the final exam. Now, I mean, if for some reason we end early, is it possible we could take the final at an earlier time? I doubt it, because the final exam is 2 hours long. Because there is a piece of the exam that is this is a core course, Rowan core course. So one half of the exam has to be the Rowan math department's part of the final. That's their part of the final. I don't write that. So you must take that as part of your final. And then I have a piece, which is a multiple choice piece, which is the next hour. So it has to be a 2-hour exam. So that's why they allot the 2 hours for the final exam day, so that, especially for this course, because you need it. You need it to take it, because a final is required for this course, and this is a core course. So yes, that's why it must be done during class. And also the math department does not want the final exam to be done at any other time. Now, again, if there's a conflict and you must take it early, that's different, all right? But you can't take it later. You must take it early. And again, there are exceptions for taking it later, but it has to be a medical emergency for you personally, where, and then you have to apply to the university and prove that it was a medical emergency, that sort of thing. So final exams, I know from my own experience when I was a student, final exams are required. You could be running a 103 temperature, and the professors expect you to be there on the final exam day. It's just the way it's been that way for a century. Who knows? It's been that way for a long time. But again, if it's COVID or a real medical emergency, you're in a hospital, that sort of thing, then you or a family member must contact me, must contact the university, let them know what's going on, and some process has to be, some paperwork has to be completed so that you can finish the course at a later date. All right. So I just wanted to make that really clear, how the end of the semester is going to work, and just make sure that you have enough time to study, and again, make sure that you're up on time for both those tests. Maybe 2 alarms, maybe not just set 1 alarm, set 2 alarms, so that one doesn't work, the other does. All right, so let's get to this chapter, chapter 17. This chapter, again, if we just go back a couple slides, remember chapter 16 dealt with the personal probability way of looking at probability, the personal probability, and the several different types of biases that our brain sometimes creates to alter what a personal probability is. And in this chapter here, they're talking about relative frequency interpretation, the other type of interpretation of probability. All right. So why do we do a relative frequency interpretation? Because the circumstance in which we are calculating the probability lends itself to computing this. Relative frequency probability requires something that we can repeat, like a probability experiment, over and over again. And then we're just counting the number of times a certain event happens and divided by the number of times we've repeated the experiment. Okay. I mean, a simple example obviously would be flipping a coin 100 times and seeing how many heads we get. And that would be a relative frequency result. Okay. All right. Any questions about that? So that's what we're really talking about in this chapter is that. They talk about coincidences. Obviously, coincidence is a surprising result. All right. It seems to be meaningfully related, but there's no apparent causal connection. All right. I think you all know what a coincidence is. It looks like it may be a real thing, but it really isn't. All right. All right. Obviously, something that's coincidental doesn't mean it will never occur. It could occur. All right. It could occur. So even if it's not probable, the fact that it occurs still means it could be a coincidence. All right, and then basically you look at things like playing the lottery, the fact that you hear of individuals who win the lottery twice, all right? And you may think, yeah, for that specific person, it's highly unlikely that that would happen. But for an entire population, for many, many repetitions of the lottery, it's actually not that uncommon for sometime for somebody to win the lottery twice. It will be a possibility. Okay. So it says here, there's at least a 1 in 30 chance of a double winner in a 4-month period for a lottery. Now you might think that's crazy, but yeah, that's because they do happen. They do happen. All right. And it says it's a 50-50 chance there will be a double winner in a 7-year period somewhere in the United States. So although for a specific person it seems highly unlikely, if you take the entire population, it's not as unlikely as it may seem. All right. Also, this idea of this birthday problem. The idea that if you have 23 people, there's a little more than 50% chance that at least 2 people of the 23 people will have exactly the same birthday. When we say birthday, we mean the actual day of the birth. All right, not the year, but the day. Most people think it's very highly unlikely that can happen, but actually, with 23 people, there's a slightly over 50% chance. It's actually the probability is actually 0.507, and they show you in this problem how to calculate it. You're not responsible for the calculation, but you should know this. Sometimes I throw this question into the third exam or the final exam just to make sure that you've read this chapter. That there is, if you have 23 people, a minimum of 23 people, then at least 50%. There's at least 50% chance that at least 2 of those people will share the same birthday. Most people think it's like, probability of that happening is like, 1% or 2% or something like that. There's actually over a 50% chance. Those coincidences only seem improbable. Coincidences seem improbable only if we ask the probability of that specific event occurring at that time to us. Get the idea? So something seems to be improbable because of the idea that for that thing to happen to us at that time seems highly unlikely. But again, if we consider it in terms of the population as a whole, it's not as unlikely as it may seem. Right? That's really what this chapter is all about. I know it seems kind of silly to go over this, but this is what this chapter is about, so I have to go through it. All right, now, there are people who have studied the psychology of probability and how it affects, how different things affect our assessment of the long-term frequency of an event, okay? And so there's different fallacies that sometimes people come up with, which try to explain why something happens. And one of these is called the gambler's fallacy. Now, what is the gambler's fallacy? Now, what we just found out is that if we repeat an experiment over and over again, this is the relative frequency approach to probability. If you remember, we talked about this earlier. If we run the experiment often enough, the relative frequency probability will come very close to the true probability. That is, if we, let's say, flip a coin 1,000 times or 10,000 times, we'll find that the probability of getting heads through the relative frequency approach will be very close to 0.5, which is obviously the true probability of getting heads when we flip a coin. So we should get, if we flip the coin 1,000 times, we should get pretty close to 500 times. No matter who flips the coin 1,000 times, it's going to be pretty close, 500 as the answer. So now, we would expect that for many, many flips of the coin. We would not expect it, however, if we were just flipping the coin 10 times. We would not expect 5. Sometimes we might get 8. Sometimes we might even get 10 heads. It's possible, right? It's, even though it's not likely, it's possible to get 10 heads in a row. So in the short term, we would not expect it to be necessarily close to the true probability if we just flip the coin a few times. However, the gambler's fallacy says that many times people apply this rule that the long-term frequency approaches the true probability. They apply it to the short term. They apply it to the short term. For example, let me give you a good example. Basketball player, right? You know, you probably think about this all the time. Some basketball player is at the free throw line, and they throw in 30, 40, 50 straight balls into the net. All right. In other words, 30 or 40 straight free throws are good. Right? They're not missing any of them. Now, most people will think that they're due to miss one. They're due to miss one. Why? Because they look back and see over the last 30, they haven't missed one. So they're due to miss one. This is the gambler's fallacy. They're thinking over the short term, the person should be going at their free throw average over the short term. Okay? And so if they're an 80% free throw shooter and they've made 100% of their of the last 30 of their free throws, they're expecting one to be missed soon. This is the gambler's fallacy. This is the fallacy to think that because they're an 80% free throw shooter, they're due to miss one soon. All right? What they don't realize is that there are runs that people can make. There are these runs over the short term. You could have 30 straight free throws that go in. So these runs can happen, and they have nothing to do with the long-term overall frequency of getting a free throw in. All right. It's just over time, you'll see people doing these sort of runs. If flipping a coin, if you get 10 heads in a row, they'll say, oh, you're definitely, they'll say something like, there's a 90% chance you're going to get a tail next time. But as we know, that every flip of the coin is independent of the last flip of the coin or the last 10 flips of the coin. They think that because there's a 50-50 chance, the 11th flip of the coin, there must be a very high chance that the 11th flip of the coin is going to be tails because they got 10 heads before that. So that's called the gambler's fallacy, thinking that over the short term, you should see that same long-term average. And that's not necessarily true. All right. So this is something that I usually ask about during a test or the final exam, but just know that's what it means. And why do they call it the gambler's fallacy? Well, because just think of a gambler, right? They're sitting in a casino and they're playing some game or something, and they keep losing and losing and losing. And the reason they keep going is because they know the law of averages is going to catch up to them, right? Quote unquote, the law of averages is going to catch up to them, and they're going to win soon. And they keep playing and playing and playing. But that's not how games of chance work. They're independent. Each repetition of a game of chance is independent of the previous attempt. Okay, so you have to be careful when you determine long-term probabilities. You don't want to apply them to the short term, where in the short term we could have different results. All right. Any questions about that? That's the gambler's fallacy. So that's why gamblers fall into this trap, thinking that the law of averages is going to catch up to them in the short term. There's no such thing as the law of averages over the short term. All right. There's no such thing as that, because if you're dealing with events that are independent of one another, the law of averages does not apply over the short term. All right. There's no such thing. All right. And this is what they're saying. Independent chance events have no memory. All right. It's not like each time we flip a coin, there's something about the coin in which it remembers what just happened. All right. That's not the case. All right. So this string of good luck or bad luck, all right, in a casino, all right, it doesn't change the probability that of the next gamble, what the next gamble is. All right. It doesn't. There's each independent play of the game has nothing to do with the previous plays of the game. There's no memory. So that's an important thing to know. All right. Now, gambler's fallacy only applies. This is a question that could have show up on your next test or final exam. The gambler's fallacy only applies to independent events. Think about that. What I've just said is that if you flip a coin 10 times and you get 10 heads, it doesn't mean there's a really high probability that the next flip of the coin is going to be tails. Right? Because each flip of the coin is independent. It doesn't matter what just happened. So the gambler's fallacy applies only to independent events. However, if an event is dependent on what just happened, then it does make sense. It does make sense to think that what just happened is important for the next play of the game. But for example, I mean, if you want to consider a casino game, the game 20, the game what's the name of that game? I forget the game where we have to get 21 to win. I forget the name of it, and they use 5 decks of the cards. Well, if you're able to count cards and keep track of the cards that have already come out, then you'll be able to have a higher probability of guessing what the next card is. I hope you get the idea of what I'm talking about. That's a case where the next play of the game is dependent on what just happened. Then the gambler's fallacy doesn't apply. Then it does logically make sense to think about what just happened, right? So if the current play of the game is dependent on what just happened previously, then there's no gambler's fallacy. The gambler is actually being logical, all right? That's why this whole idea of counting cards, right? Casinos hate that. They don't want you to be playing a game where you can count cards, and the counting cards puts you at an advantage. So this is an important thing. The gambler's fallacy, where you misapply a long-term probability to short-term events, okay? That only applies to independent events. That's why it's a gambler's fallacy. Because if events are dependent on one another, there's no such thing as a gambler's fallacy. All right. Any questions about that? I hope I was clear. And then they use the example down here about knowledge of what cards have already been played can affect how likely is that you're going to receive a certain type of card in the game that you're playing now. All right. That would be true for poker too. Poker or anything like that. Okay. Confusion of the inverse. Now, what does this mean? Well, sometimes we have to think about the probability that we're interested in, and then sometimes we're given the inverse probability. This might be a little confusing to you. This is an example of this here. A patient has a lump, right? So patient comes into the doctor's office, has a lump, and the physician assigns a 1% chance that it is malignant, all right? So 1 out of 100 people who come into the office, the lump is malignant. That means 99 out of 100 it isn't, all right? So you think, oh, okay. Now, mammograms, so let's say the lump is in the breast, all right? Mammograms are 80% accurate for malignant lumps and 90% accurate for benign lumps. What does that mean? All right. 80% that means if we have a malignant lump, the chance that the mammogram is correct is 80%. All right. Same thing with benign lumps, 90% accurate in picking benign lumps. So a mammogram indicates that a lump is malignant. What are your chances is truly malignant? All right. Now, most physicians say about 75%. So if you get the mammogram back and it says you have a that lump is malignant, most doctors say that means there's a 75% chance that the test is correct, 25% chance that it's wrong. But in actuality, this test is only 7.5% accurate. 7.5% accurate, given the information here. Now, I'm not going to show you the mathematics of how they came up with 7.5%. But what's happening here, most physicians are coming up with a probability for the wrong, coming up with an answer for the wrong probability. Okay, it says here that physicians were confusing the probability of cancer given a positive mammogram result with its inverse. The probability of a positive mammogram given the patient has cancer. So don't worry about the calculations of this. Just know that sometimes what happens is the doctor is looking at the wrong probability. It should be the inverse of it, all right? So don't worry about understanding what this means here. If I was teaching this in a regular statistics class, this would be something called Bayes' rule. It would be some sort of complicated calculation that you can make these determinations. This is not part of this class. Don't worry about it. The only thing they're saying here is that sometimes the reason why the doctor gets these percentages wrong is because they're looking at the wrong probability, they're looking at the inverse of what they really are thinking. All right, so that's all you need to know. You don't need to know anything else about that. All right. I mean, they give an example here, but again, don't worry about it. All right, I'm not going to test you on these sort of calculations. But let's just take a look at this table just to sort of understand what they're saying. So here is 100,000 people, women. Now you know how to read this table, by the way, don't you? 100,000 people. This is one of these contingency tables. And there's two different variables. There's whether the lump is actually malignant or benign. That means it's truly cancerous or not truly cancerous. And then on top here is the test, the mammogram. The mammogram results. The mammogram results are either going to show malignant or benign. All right. And remember, the mammogram is not 100% accurate. That's true. That's true for any test, by the way, including COVID tests. COVID tests, if you get a positive result, doesn't mean you have COVID. There's no such thing as a perfect test for anything. But anyway, we know that 1% of people in general, if they have a lump, 1% of those are malignant. So we have 100,000 people who have a lump, okay? And 1,000 of them, which is 1% of 100,000, 1,000 of them will be malignant, 99,000 will not, all right? See how they came up with these numbers? 1% of 100,000 is 1,000, 99% of 100,000, 99,000. All right. Now, suppose if you actually have a malignant tumor, 80% of the time, so this is how you read this. If you have a malignant tumor, actually do 800 of the 1,000, 80% of the people who have malignancies will actually have a positive test. That's what it says here. So we would say the probability of having a positive test given that person had malignant tumor is 80%, 800 out of 1,000. In the same way, out of the 99,000 here, it said, I think it said 90% of the people who don't have a tumor, 9,900 out of 99,000 show a positive test, and here's 89,100. Now here we go. 90% of 99,000 is 89,100. Okay, so out of the 99,000 people who don't have a benign tumor, the test shows benign. So that means that the test is 90% accurate if you have a benign tumor and 80% accurate if you have a malignant tumor. All right. Now, what if we ask the following question? All right. Out of all the people who took the test that shows malignant, that they had a malignant tumor, so if the test shows you have a malignant tumor, how many actually had the malignancy? 800 out of 10,700. That's 7.5%. So you see that the doctors, when they came up with 75%, which is actually close to the 80%, they were looking at 800 divided by 1,000. They were looking at that probability. The probability that the test is positive, all right, from the group of people who have malignant tumors, right? And what they should have been, what they were really being asked is, out of all the people who showed a positive test, how many actually had cancer? Only 800 out of 10,700. This is the more important probability. Now, again, I'm not going to ask you to calculate this, all right? Although I could, you know, in some way, because we've done this before, I could ask you to calculate this, say, you know, knowing that there's 10,700 people who have a positive test, how many actually, out of those, how many actually had cancer? It'd be 800, and the probability is 800 divided by 10,700. I mean, you could do that, but do you see, I hope you see that the doctors, when they say 75%, they're looking at the wrong probability, all right? And the probability they should be looking at is this one here. So this one here is basically saying that if we just look at the people who got a positive test, what is the probability that one of those people actually has cancer? It's only a 7.5% chance. Okay. So these tests aren't as accurate as they seem to be. But anyway, this is an example of confusion of the inverse. They're asking the wrong probability question. They're asking the reverse of what should be asked. And again, don't worry about it. You just have to know that what confusion of inverse means. All right. Now, false positive. All right. Now these definitions, sometimes I do ask about these. So let's just talk about this for a second. I want to spend a little time on this so that you understand the definitions. What is a false positive? So what is a false positive? Means that you came back with a positive test. Now, positive test for medical situation would be, it says you have the disease. All right, that's what positive, right? If you got a positive COVID test, it means you have COVID. False positive means that the test comes back positive, but you really didn't have the disease. All right, that's a false positive. Everybody clear on that? Now, what is a false negative? That's the other one. False negative means the test came back negative, but you actually have the disease. In both cases, there was a mistake. The test made a mistake. So false positive means you don't have the disease when the test says you do. And a false negative is you do have the disease when the test says you don't. All right, so let's look at these definitions here. Now remember, you have access to your book and you're being asked any questions about this. So the base rate, what is the base rate? Now there's three different probabilities that are being asked in this sort of situation. All right, there's a base rate. It's the probability that you're likely to have disease without any knowledge of your test results. Well, let's go back to this example. The base rate is this number 1%. All right, that's the probability of getting the disease. 1 out of 100 people, or 1,000 out of 100,000 people. 1% is the probability that if you have a lump, it is cancerous. That's called the base rate. Right? Now, there's two other types of definitions. The sensitivity of the test. It's the proportion or probability of people who correctly test positive when they actually have the disease. The sensitivity of the test. Now, the sensitivity and specificity of the test are correct probabilities. There's no mistakes here. What we were just talking about earlier is false positives and false negatives. Those are the mistakes where the test is giving you the wrong probability. The sensitivity of the test is the proportion of people or the probability that when you have a positive test result, the person actually has the disease. All right. So it says here the proportion of people who actually have the disease. All right. So the proportion of people when they actually have the disease who correctly test positive. So this is sensitivity of the test. How sensitive is the test? Let's go back to that table and see what the sensitivity is. Proportion of people who test positive when they actually have the disease. If they have the disease, here we go. If they have the disease, where is that? It's the first row. There's 1,000 people who have malignant tumor. They have the disease. Okay. How many show that they test positive? 800. So 800 divided by 1,000 is 80%. That is according to this definition, the sensitivity of the test. So you go to the row where the people have the disease and then determine how many had a positive test. All right, 1,000 people have the disease, 800 had the positive test. 800 divided by 1,000 is 0.8. 0.8 or 80% is the specificity of this test. Excuse me, the sensitivity of the test. Let me not let's say it again. The sensitivity of the test is 80%. The specificity of the test is the proportion of people who correctly test negative when they don't have the disease. Back. They don't have the disease. 99,000 people don't have the disease. And the test shows benign. That's the number here that we're looking for. The 89,100 divided by 99,000 is 90%. So according to this definition, the specificity of the test is 90% or 0.9. Okay. So if I gave you a table like this and asked you for the specificity of the test or the sensitivity of the test, based on those definitions, hopefully you'll be able to use your calculator and come up with those numbers. And then the baseline, again, remember, is this 1%. That's just the overall percentage of the population that has the disease without dealing with any tests. There's no test information, just in general, what is the proportion of the population that has the disease? 1% or 0.01. That's the baseline. And then we have the false positives, it's false negatives. All right. So what's the probability of a false positive? Okay, what's a false positive? it means that you have a positive test result, but you don't actually have the disease. So a what's the probability of false positive? Well, how many people have the, so it says, so what is it again? It is, the test result is positive. So we have 10,700 people who have a positive test result. Now, how many people do not actually have the disease? 9,900. So 9,900 divided by 10,700, that gives you the probability of a false positive. Or if you just asked for out of 10,700, how many have false positives, the answer is 9,900. Does that make sense? The test comes back positive. Those malignant, that's 10,700 of those people. And how many mistakes were there? 9,900 mistakes. Okay. How about a false negative? Now the test comes back negative. There's 89,300. False negative means that the test says you don't have the disease when you actually do. 200 divided by 89,300 gives you what? Gives you the probability of a false negative. All right. Sort of understand what I'm saying here? All right. So that's something I could ask. But as far as the confusion of the inverse, I'm not going to ask you about that, except for knowing that people tend to, when they're thinking they're asking for a certain probability, they're really looking at the wrong one. All right, there's a question from somebody. I hear somebody saying something. Any questions? All right. All right, and then in this little section in here talks about, I was talking about basketball and free throw shooting or shooting baskets, and over the short term, this is the whole idea is over the short term, you can see these streaky shooting type of things. All right. And then here they're talking about use expected values to make wise decisions. Remember what an expected value is, right? It's the probability times the value. And then you add up all the values times their probabilities, and you get what's called the expected value. So let's look at an example of this here. So you have different alternatives here for some situation. Alternative A is that you're given a gift of $240 guaranteed. So you're being asked to make a choice here. So $240 guaranteed. B is you have a 25% chance of winning 1,000, 75% chance of getting nothing. C is a sure loss of $740, and D is a 75% chance to lose 1,000, 25% chance to lose nothing. Now, let's look at alternatives A and B here. Can somebody tell me which of these two alternatives, A or B, would you or most people choose? In other words, somebody came up to you and said, I'm going to give you $240 guaranteed. Or B, you have a 25% chance to win 1,000, a 75% chance of getting nothing. What would you choose?
A.
A. All right, anybody else? A? Most people would choose A. Anybody else want to confirm that, or would you choose B?
I would choose A.
All right. Now, why would you choose A?
I'd rather have $240 and have a less than likely chance to win 1,000.
Right. So this is how most people would come up with this. They'd say the sure thing, right? I'm going to go with the sure thing if it's a positive gain. However, B is better as far as long-term chances of winnings. If you multiply the probability times the value, so 25% chance of 1,000 is $250. 75% of zero is zero. So $250 plus zero is $250. The expected overall long-term gain is $250. So B is actually the better choice mathematically. But most people will go for A because they know they're getting the 240. Even though over the long term, B is the better choice. That's what they mean by expected value. You take your probability and multiply it times, or percentage, and multiply it by its value. In this case, there's two choices. Either you win 1,000 or you don't. You multiply the probabilities by each of those choices and then add up those products. And that's your expected gain, $250. So logically, you go for B. But people don't do that. They look at guarantee. They're going to go for that. Now, let's look at C and D. Either you have a sure loss of 740, or D is 75% chance of losing 1,000, 25% chance to lose nothing. Okay, which one would you do, C or D? Either you're going to have either you have to pay somebody $740 guaranteed, you have to do it, or there's a 75% chance of losing 1,000, 25% chance of losing nothing. Which one would you go with?
I would go with C.
Okay. Now that you know about calculating expected values, right? I had not told you anything about it, you probably would have gone with D. Why? Because you want to have a chance of not losing anything. Most people would go with D. But if you calculate the expected loss of D, it's actually worse. The 75% of 1,000 is a $750 loss, and 25% of 25% of 0. So the expected loss in D is $750, which actually is worse than the 740 sure loss. But most people don't want a sure loss. They want a chance of not losing. So most people would go with D. But the actual answer is C. You should go for C because the loss is less. All right, so this is an example here of how expected values should give you the right decisions, but most people choose the opposite because of because people either want a guaranteed gain or they want to avoid a guaranteed loss. That's really what they're referring to here. All right, and then they show you what they're talking about. All right. All right. So anyway, we'll skip this last example here. And this, of course, I was telling you about Bayes' rule, or Bayes' formula earlier, and this is what it looks like, and it looks horrible, right? It's actually not horrible if you learn to use it, but I don't even teach this in the Stat 1 course at Rowan. A person has to be pretty good mathematically, pretty comfortable with complicated formulas to be able to feel comfortable in using this. And, I don't know many students who do. So this is not something I typically teach, even in the Stat course, but this is what it looks like. And by the way, this formula here, this P with the A1 and the bar B, is the inverse of this one up here, probability of B given A1. And that's what they talk about probability of inverses. If I was teaching this Bayes rule to somebody, then the probability of inverses would make more sense to them. But definitely not going to be doing it here. All right, so that is chapter 17. And the most important things to remember about chapter 17 is this idea here of expected values. You should know that. Let's see, I just want to, now, also this idea of these three things, the base rate, sensitivity, and specificity, you should know how to calculate those, and also false positives and false negatives. You should be familiar with that, okay? So make sure you know those ideas also. So those are the types of things I could test you on, and also the gambler's fallacy too. That's also important. Any questions about chapter 17? Always good to read the book if you can. gives you a fuller explanation than these slides do. But and I'm pointing out those things that I could test you on in the next test and also on the final exam. All right, so let's stop sharing this. We'll go to the next chapter. So now we've completed everything that we need for the quiz. And now we're going to go to chapter 19. And hold on a minute, something went wrong here. All right, chapter 19. What happened here? That's not right. All right, so give me a second here. Something went wrong. Just check to see what I have here. Oh, there we go. So my computer did a funny little thing with chapter 19, and now I have it. So sorry about that. There we go. All right. Now this chapter actually is very important. This is dealing with sampling. Sampling is going to be the basis for what we're going to be talking about for the rest of the course. Now that we're away from all this probability stuff, we're now going to be talking about sampling. So I'm going to actually skip the thought questions at the beginning. I want to get right to it, if you don't mind. You can, of course, look at these later. All right, now, it says here, the purpose of sampling, if it's done correctly, is to allow us to work backwards from the samples to the population. In other words, we know that we have a population of people and we draw a sample from that population, right? So we're going from the larger group and picking a subset of that larger group, and we call it a sample. Then we do some work, some calculations from that sample. We might find the mean or the median or the standard deviation, whatever it might be. Then we want to make some interpretations and generalize that to the whole population. We're going to say, let's say we found the mean of the heights of people in a sample, and we come up with a certain average height. We would like to say that that average height of the sample might be close to the average height for the whole population. That's really what we're interested in. We want to know something about the population. So we take a subset of the population, do some work with it, come up with some statistics, and then say, all right, I think this is a good estimate for that same thing for the whole population, whether it's the mean, the median, or standard deviation, whatever. All right. The question is, how good is that estimate? Is it a great estimate? Is it a good estimate? Is it a bad estimate? Okay. And if all of you in this class did that same sort of sampling, let's say we had 1 million people in the population and we sampled 100 people, and each of you randomly chosen, and remember random sampling, simple random sampling, cluster random sampling, stratified random sampling, systematic sampling, whatever sampling technique we used. And if all of you came up with 100 out of the 1 million for your sample, the question would be, would you all get different results? And the answer is, yeah, there's a good chance that you probably all get different answers, different estimates. So the question is, which of those estimates for all the people in the class, which are the good ones and which are the not so good ones? Are we able to tell? Okay. So the dissimilarity among samples. So all of you in this class, let's say there's 30 of you in this class, okay? And you all did the same type of sample from the same population and you get different answers. How can we work with that? How can we actually come up with an estimate for the population when everybody's going to get different answers? Because everybody's going to have different samples. Can we at least come up with an answer that's within a range so that the population is somewhere in that range? Can we do that? That's a possibility, right? So it says here, suppose most samples are likely to provide an answer that's within 10% of the population's answer. Can we work with that? Well, possibly, right? So if all the samples, let's say you're coming up with the mean height of 100 people, and everybody in this class does this, and they'll come up with different mean heights. If you kind of knew that all of your answers were most likely within 10% of the population's true mean height, would you be okay with that? Would you be happy with working with your estimate? And the answer is probably maybe, right? You might be. So that's how we're going to be looking at it. We're going to say, instead of thinking that our sample estimate is perfect, we're going to say, all right, how close is it to the true population value? Is it within 5%, 10%, 15%, something like that? And if it's within a certain percentage, then we're going to be hopefully happy about that. All right. And that's going to be the way we're going to estimate for the population. We're going to look at intervals of values. All right. And this is an example here where 40% of a population carry a certain gene. All right. So they have these X's that represent people. So all these boxes and smiley faces in here represent people in the population. And some of them have smiley faces, which means they don't carry this gene, which I'm assuming causes some sort of disease or problem. And if you do carry it, you get a big X through a box. All the X's here represent people who have that bad gene, and the smiley faces represent people who don't. Okay, so it says here 40% of the population carry a certain gene. You did a sample of 25 people. Suppose 4 of you randomly sampled 4 people out of the population. I'm assuming 4 of you each sampled 25 people out of the population. But for example, I'm just going to pick some names here. Anika took sample number 1, and she counted the number of people out of the 25 who had genes. So she counted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there was 12 of these boxes with crosses in them, which indicates that 12 of the 25 people chosen have the gene. So your estimate of the proportion of people who have this gene is 48%. 12 divided by 25. So Nika, that would be your answer. All right, Diana, out of her 25, if she counted the number of boxes that have X's, she would come up with 9 of them. 9 divided by 25 is 36%. So that's her estimate. Colin, he took sample 3, and he counted the number who had the gene, and there was 10 out of the 25 who had the gene, if he counted the number of these boxes. So 40% of his estimate is his estimate for the population. And Danielle, her sample 25, she had 7 out of the 25 who carried the gene. There's 7 of these boxes, and that's 7 divided by 25 is 28%. So you can see all these people, all 4 of you, came up with different answers. All right. Now, one of the questions you might ask is 25 large enough sample, right? That's one issue. Is it large enough? But given that you all took 25 people, and this is your answers, these are the different sample estimates. The fact they're all different is what we call sampling variability. So this term, sampling variability, means that given if a sample is repeated over and over again, we would get different sample estimates. So if we're interested in the proportion of people in the population who have this gene, and we just happen to know it's 40%. You can notice that the samples all have different values, and there's only one of them that matches perfectly. That's the sample number 3. That was Colin's estimate. But Colin, you don't get a gold star for doing this. It was just by chance you got this particular one that matched the population. The other three people, Anika, Diana, and Danielle, did not make a mistake. They didn't make any mistakes. The fact that they had estimates were different than 40% is just due to random chance. It's just due to the fact that they chose those particular samples. That's the ones that they got. So each sample will have different estimates, and that's called sampling variability. All right? And it may or may not match the actual population estimate. Now, in reality, when we're doing sample estimates, we do not know the population estimate or a population value. We don't know the population proportion. If we did, why would we bother sampling, right? We wouldn't bother with it. In most cases, we don't know. So that's why we do the samples. All right. So what are the conditions for finding sample proportions? So suppose that's what we're measuring, the proportion of people who have a certain characteristic. Well, number one, there exists an actual population with this fixed proportion. That makes sense, right? We need to estimate it. So there is an estimate. There is something out there. There is a fixed proportion of people who have this trait. Or it says here there exists a repeatable situation for which a certain outcome is likely to occur with a fixed probability. All right, fine. All right, so basically what they're saying here is there is a true population proportion. That's what they're saying. All right, so if we're going to do a sample proportion, we want to make sure there's actual population proportion that's out there. Number two, that we randomly select from that population that has that trait. All right, obviously. You need to take a random sample, or the situation repeats itself many times with an outcome each time independent of all other outcomes. That's a possibility too. And it says the size of the sample, number of repetitions, is relatively large. What does that mean? It says it's large enough to see at least 5 of each of the 2 possible responses. All right. So basically, we need to make sure that the size of the sample is large enough. All right. That's really what they're saying. Now, the rule in which how big is debatable, but just know that the size of the sample has to be large enough. Okay, and here are examples of using sampling to estimate a population proportion. For example, pollster wants to estimate the proportion of voters who favor a certain candidate. They don't know. They're not going to poll every single person who will vote. They can't do that. They're not going to be able to do that. Too expensive. So who are the ones who are going to be contacted? It would be those voters, right, or potential voters. And they're going to be asked their opinion about which candidate they favor. So they're going to do a poll. So if they have 10 million people in a population, they may take a poll of 1,000 people. And they ask them, which candidate do you like, candidate A or candidate B? You make a choice. And then once all the information is collected, the pollster will add up all the people who like candidate A, for example. All those people like candidate A divided by all the people who were asked would give you the proportion of people in the sample who like candidate A. And then the pollster would use that as a possible estimate for the proportion of people in the whole population of voters who like candidate A. Same thing with television ratings, right? You're not going to contact every single person who watches a television show. What do? You find a sample of people and ask them about the television show, if they like it or not. And you find the number of people who like a particular television show. All right, consumer preferences, that could be about soft drinks or anything that people buy. People can be asked about whether they like one thing versus another. You just count the number of people who like that, divide by the number of people being asked. All right, so you get the idea here, right? These are all examples of cases where we would possibly be interested in taking a sample proportion of people who like something versus not liking something. All right. I told you there wouldn't be much use of formulas in this course, but there is a couple formulas that would be worth knowing. And again, because you are taking your tests remotely, and you can use your textbook, there's no reason why, as long as the formula is not terribly bad, you could come up with an estimate of something. Now, for sample proportions, if you have a sample proportion of people who like a certain trait or candidate, whatever you are measuring, remember you're just counting the number of people who like that soft drink or candidate, whatever it might be, and divide by the number of people that you asked, and that's your sample proportion. And we would say that sample proportion is the mean, an estimate of the mean of the true proportion, right? The average proportion. Now, what is the standard deviation? Remember, the standard deviation is considered to be sort of the average spread of the data. How would you calculate it? Okay. Well, it says here, if numerous samples or repetitions of the same size are taken, the frequency curve made from the proportions will be approximately bell-shaped. All right. Now, don't worry about this too much, but if I was going to ask you what is a good estimate for the standard deviation of for sample proportions, well, how would you come up with it? It says to take the square root, and you would take the true proportion. Now, what is the true proportion? We don't know, so we would use the sample proportion as an estimate. So we put the proportion in here, inside the square root, in it as a decimal. So if the proportion is 60%, we would put 0.6. Then we would multiply by 1 minus that proportion. So if the proportion is 0.6, 1 minus 0.6 is 0.4. And then we divide by the sample size, the number of people in the sample. So we take that ratio and take the square root of that whole thing, and that would be a good estimate of the standard deviation or spread of these sample proportions. Right? How spread out are all these possible sample proportions? And this would give you an estimate of that. All right. Let's see an example of what they're talking about here. It says, suppose 40% of all voters in the US favor candidate X. Pollsters take a sample of 2,400 people. What sample proportion would be expected to favor candidate X? Now, the sample proportion could be anything from a bell-shaped curve with a mean of 0.4 and a standard deviation of what? Well, the standard deviation is if we put 0.4 inside the square root and then 1 minus 0.4 divided by 2,400 people in the sample, you would get 0.01 as the standard deviation. Okay. So the mean is 0.4, standard deviation is 0.01. Okay. Now, obviously, we don't know 40% of all voters favor candidate X, but they're saying here, suppose that is true. 40% of all voters in the US favor candidate X. Then we would say, what's the probability of that the sample proportion that we get in our sample is between certain values? This is what they're asking. Now, where did they come up with this? Do you remember? Anybody remember what the 68%, 95% is? Where do they come up with that? Maybe you might remember. Remember the empirical rule that we talked about earlier in the course? I think we talked about that when we talked about bell-shaped curves. The 68%, all right, if it's a bell-shaped curve, 68% of the data is going to be between plus or minus 1 standard deviation from the mean. 95% is between plus or minus 2 standard deviations from the mean. So how did they come up with these numbers here? They took the mean is 0.4. Now, why did they say 0.4? Because if 40% of all voters favor candidate X, that is the mean of the population. That's the mean proportion. 0.4 standard deviation is this square root formula. We came up with 0.01. That's our standard deviation. So The mean plus or minus 1 standard deviation is 0.4 minus 0.01. So 0.39 or 39%. 0.4 plus 0.01 is 0.41. That's the 41%. That's where they came up with this. 95% chance it's between 2 standard deviations of the mean. But if 1 standard deviation is 0.01, 2 standard deviations is 0.02. 0.01 times 2. So 0.4 minus 0.02 is 0.38. That's 38%. 0.40 plus 0.02 is 0.42. 42%. That's where they came up with these numbers. All right. So Anika, and Diana, and Colin, and Danielle, and everybody else in the class, if you took samples, if each of you took samples of 2,400 people, okay, and came up with the sample of the proportion of people who like candidate X for each of the samples, you all get different answers. But we would expect 68% of you, if there was maybe thousands of students did this, 68% of the students would have samples between 39% and 41%. And 95% of the students would have sample proportions between 38% and 42%. Do you get the idea? We would expect a high percentage of people to have sample proportions between these values, ones that you actually get from your samples. All right, you sort of get the idea of what I'm talking about here. I hope you do. This is the sampling variability we're talking about here. But if the samples can all be put on a bell-shaped curve, you can come up with these probabilities. So 95% chance that the sample estimates that you guys come up with are between 38 and 42%. That means there's a 5% chance that some of you will have sample estimates that are less than 38% or greater than 42%. That's what it means. Some of you will have estimates out of that, but most of you, 95%, will have estimates between 38 and 42%. And that's pretty good. That's pretty good. And that's why we do sampling, because we can come up with these ranges of possible values and give a probability or chance of that your estimates will be within a certain percentage of the true population proportion. Okay. All right. So that's with bell-shaped curves. That's the only one that we're going to talk about in this particular. It looks like we're done today. I'm sorry that I got carried away here. And so we're going to be looking at finishing this up next time, this chapter. We're also going to talk about StatKey next time. We're going to show you an introductory video on StatKey also. And then we're going to have our quiz. All right, the last 20 minutes. So this is a chapter 19. I would recommend that you read through it. Again, it may not make much sense to you at first when you read through it, but just do the best that you can. When we use StatKey, it will become easier to understand what I'm talking about today. All right, so we'll finish up chapter 19 and then go right into StatKey. And again, don't worry about this if it's a little confusing to you. It will get better as time goes on. All right, so that's it for today. Any questions? All right, so everybody's dropping out without saying goodbye, but that's okay.
I'm going to send you an email, Professor.
You're going to send me an email? Okay.
Yeah.
All right,